I've got a truly amazing piece of cloud security research for you today. The hunt for ALBeast, a technical walkthrough from Liad Eliyahu. I'm sorry if I've butchered that, Liad. And Liad works for Miggo.io, so go check them out after you've listened to this blog post. Now, what makes this research truly amazing is three things. One is it's super easy to execute the attack. There's no shellcode required. Basically, any AWS security engineer can go ahead and do it. It pokes holes in the AWS shared responsibility model, which I love and always find enjoyable, and it affects a lot of applications. There's some data within the blog post that we'll go into. So let's get stuck in. But first, a good place to start is understanding how ALBs do authentication, or what's this all about. So the idea here is that you can configure an application load balancer in AWS to securely authenticate users as they access your applications. This enables you to offload the work of authenticating users to your load balancer so that you can get on and focus on your business logic. So the idea is make it truly easy for developers to do authentication, which is great in theory. We'll see how that breaks down a little bit later on. But I wanted to show you a diagram. So here's kind of how it works. So first, a user makes a request to the ALB. They get authenticated by the ALB and the identity provider. The ALB then sets a cookie in the user's browser, and then the next time a user makes a request to the app, they include a JWT from the cookie. The app validates the JWT and they get back a response. This, in theory, should make life much easier for the application developer because they're not having to do all of the authentication bits. Now, this blog post is about a discovery of an unexpected security flaw in this process. So we identified a critical configuration-based vulnerability that enables authentication and authorization bypassed in applications using the AWS ALB authentication feature, provided they do not comply with updated AWS documentation issued after the Miggo disclosure. This vulnerability allows attackers to directly access affected applications, particularly if they are exposed over the internet. They identify three separate issues. Issue number one is a misconfiguration. Applications misconfigured as ALB target groups and accessible directly. So if they're accessible through the load balancer, but also somehow around the load balancer, bypassing the ALB can be exploited. Attackers can use a shared public key server for all AWS accounts in the region to set an arbitrary key ID. We'll go into what this means later, but you can see this endpoint is basically available to everyone. Misimplementation. Until recently, the AWS ALB authentication docs did not include guidance on validating the token signer, a crucial field for ensuring that the token was signed by the trusted ALB, so the correct ALB. Without this validation, applications might trust an attacker-crafted token or an attacker-crafted ALB. The absence of this best practice leaves applications vulnerable to ALBeast attacks. Note that ALB tokens do not contain the audience field, which is more typical in JWTs. And then the final or third issue is issuer forgery. An attacker can forge an authentic ALB signed token with arbitrary identities, claims, and issuers using its controlled ALB. This means that misconfigured applications that verify the identity of the issuer are also vulnerable to ALBeast. They've reported all of these issues and have been collaborating with AWS, and all of these issues have been solved to some degree. We'll figure out what that means a bit later on. Some interesting stats. Miggo identified over 15,000 potentially vulnerable applications out of the 371,000 that they scanned. Out of multiple implementations and open source projects, we've encountered the vast majority lack the signer validation implementation, so that's issue number 2. A significant share does not restrict access according to the latest documentation, so they allow both around and through the ALB. There are 2 AWS ALB authentication mechanisms, both of which make applications vulnerable, OIDC and Cognito. Miggo has a bunch of recommendations for AWS customers. Number 1 is validating the signer field of the token, and AWS has issued updated recommendations for how to do that. So you can see here, they look for the signer field and make sure that the signer is as expected, and the expected signer is defined up here. So essentially what they're saying is make sure it's coming from the right load balancer, the load balancer we expect, and not someone else's load balancer. Ensure that applications receive traffic exclusively from the trusted ALB. The third issue around forging the issuer field, AWS apparently deemed not to be a vulnerability. They state that the service operates as intended and that the shared responsibility model applies to this issue, implying that the application should follow the latest documentation by updating their code and security group configurations. There's also some recommendations for AWS, a couple of which they have already implemented, specifically notifying users regarding the exposure of ALB connected applications in target groups that receive traffic from other sources other than ALB, and updating the docs around the signer field. I think they've got one more recommendation, which is adding the audience field, which didn't get implemented by AWS, as we talked about above. Just quickly about some of the documentation. In trying to understand this issue, I found this blog post on how to use application load balancers and Cognito to authenticate users for your Kubernetes web apps. It's from 2021. And in here, there's a bit of code to do the validation that we've been talking about. It doesn't look like it's been updated. Again, you can see there's not the 4 steps that we previously had, and there's no mention of the signer field here. So the signer is clearly not being validated. A request to this application could come from an ALB that's not intended. So that's something for AWS to go back and rectify. There's a whole section devoted to story time about how they found these issues and how they went about exploiting them. I'm going to skip the first bit and go straight to the middle, attacking applications with forged tokens. Assuming an application has not yet followed the latest AWS updated documentation and validated signer, if we wanted to target an application in US East 1, what would stop us from doing so? By configuring an ALB in US East 1 with our own personal IDP, signing a malicious token with the ALB that we created, and passing that malicious token to an application inside this header? Well, nothing, and that's exactly what they did. And if you want to replicate some of the research, they've developed 2 bits of code that'll help you. One, a Flask app that just outputs headers so you can see what's going on, and then another Flask app that mimics the code that AWS had previously used for validating signatures. So this was pre the advice of having a signer field. So you can go ahead and implement this code and try the attack yourself. If you are interested in replicating some of this research, I recommend you check out jwt.io. It allows you to decrypt JWTs and see what's inside them, play with them, etc. You might find this really handy. At this point, we were able to forge a JWT signed by AWS for any app exposed to the internet that doesn't verify the issuer field. Awesome. Then they go on to broadening the scope of the attack. It turned out that we had found a way to forge the token with an arbitrary identity for applications that implement ALB as the auth mechanism, even when deployed to another cloud provider. This vulnerability could be exploited in the following scenarios. The application could be accessed directly bypassing the ALB. The application did not verify the signer field as part of the JWT verification, and the application did not verify the issuer field, though most applications do validate the issuer IDP. We should have been satisfied, but we couldn't help but wonder, how far can we take this? We continued our research to find out if we could also forge the issuer. We first tried changing the issuer in the OIDC configuration of the ALB, but the authentication failed with a 401, and you can see them doing this here. They tried to put the issuer as Google, even though they were using their own IDP. The mismatch caused the ALB to return a 401 status code, as you expect. They did some brainstorming and they tried to understand how the cookies and IDP work, and they found out that a bunch of data was stored in the cookie. It creates a session cookie and stores the token inside the session cookie. At this point, all we needed was to find one more place where the ALB stores our data to see if we could force a desync between them. We looked in the header, which contained the JWT signed by the ALB. It had a 1-minute expiration time. Hurrah! We found another place where that data is stored. Putting our theories to the test. What would happen if we authenticated, got a session with the token inside the cookie, changed the ALB configuration, and the token then expired? We knew the ALB would have to mint a new token. Would the ALB take the issuer from the encrypted token that we have, or would it take it from the new configuration as is? Remember, the user could be set to anything. The ALB only determines if the issuer we provided is valid after it communicates with the IDP. In the session, the issuer is validated after the IDP check, whereas in the configuration, it is specified before any validation occurs. So they're saying you can set your own issuer in the configuration. To our surprise, the ALB indeed took the issuer from the configuration. So previously, the issuer had been validated This time, because the token's being refreshed and the configuration has changed, instead of taking the issuer as it was from the previous token that came from the IDP, it's taking it from the configuration that they set in their own personal IDP. In my estimation, and I'm not a security engineer, this should never happen, and this should be one of the fixes that AWS puts in place if they already haven't. In other words, we would be able to use our own controlled ALB to sign the valid token in the same region as any application we felt like attacking, and we could even control the issuer. This means we could forge a completely valid JWT token for any target application that could be accessed directly and not through the ALB. So just to summarize, we've discovered how to forge a token that would be accepted by any target application in a few simple steps. Create our own ALB in the target group pointing to our IDP. Mint a token with the desired claims. This token has a valid issuer, our IDP. Its public key is stored in the regional JWK server trusted by the target application. Reconfigure the ALB to target the issuer, wait for the token to expire, then refresh it, and the refreshed token now has the new issuer. Send this token directly to the target application by bypassing the ALB. The target application validates the issuer and confirms that all is in order. We've provided the application with a forged token, and obviously this is a big problem. They go through some of the responsible disclosure timeline. I won't go into that. It's pretty standard stuff. Go find Liad on Twitter. He's at Liad Eliyahu. Now, I don't typically do post-reading commentary, but I did want to address a couple of things in this blog and around this issue. The whole idea of making an ALB do your authentication for you is to make it truly easy to do. And as you've seen, there's a whole bunch of code you have to put in place to actually make it work. This is a big area where I think AWS or the customer could make a big impact on security by standardizing that code, stripping all of that complexity away from the user, putting it inside a library, a sidecar, or something else, just requiring some decorators in the functions to make it work, making sure that all of the validation happens behind the scenes. Another thing I wanted to talk about is this issue of giving everyone a foot gun, and then when everyone shoots themselves with it, kind of saying, hey, everyone, we gave you a foot gun, please don't use the foot gun to shoot yourself. But a better way to do it would be to take away the foot gun in the first place and not make these issues possible, or help the users in a much more standardized and rigorous way rather than just asking them to do so. Because we know that at scale, not everyone will do these things. No matter how much AWS communicates with their users and begs and pleads for them to change this configuration, there will be a bunch who don't do it, and they'll continue to be vulnerable for a long time. Remember to subscribe to awssecuritydigest.com to get the latest security articles in your email every week, and head on over to Plarion.com if you want some help with cloud security. You can grab a free trial or a demo at any time. I'm the super serious internet guy. Thanks for listening.